angle state.
So actually the single mode fibers, they go to the telescopes which are out there on the seafloor, and they are actually, this is a quantum channel we use here.
Yeah, now speak about a quantum Lego or something like that. That's why grow up and stop playing with Lego if you can just do it with this setup here.
And if the camera now works, below there's also a detector unit. So one of the photons is measured on this detector unit directly. So
it's okay.
And
This is the detector unit?
yeah, this is the detector unit. So there is, for example, from the front side you see a optical fiber input, and then there is such a polarization measurement done, and the other photon is sent over the telescopes to the other side, and there's another measurement done.
Okay. So maybe this is just really easier to see in hardware. Just feel free to come by and look at the whole thing. Also, then it glows nicely blue. We didn't hook up the power supply to the laser. It looks quite nice. And actually, you can see these photons coming out of that crystal. It's not a very faint source. It's reasonably strong. You can see it by your eye.
These cones basically with different colors. But come by and have a look.
So can we switch now back to the screen thing? Or the camera can come and look at the... so I don't know how that... Okay, so you can just have I mean, if you ask yourself how many photons are coming out, we get about 20,000 pairs per second generated, and we can do these measurements on these funny entangled states. We work at an infrared wavelength where our detectors work reasonably nicely. Also because that laser diodes, you don't get laser diodes in the ultraviolet or somewhere. We have to use basically what people build for these Blu-ray disc players.
So for the photons, you only see the pump light, which pumps not only a crystal, but the photons are transmitted are invisible to the human eye.
Okay, how do you actually do this quantum key distribution with such a gadget? So you have your source in between, and you just do a measurement now on both sides with these kits. Now you just get one of 4 results on this side and one of 4 results on that side for each pair you make, and then you do exactly the same as for this BB84 protocol, meaning that you discuss, have both parties seen or measured in the same basis, or have they seen different bases, and then they keep the cases where they have measured in the same directions for the raw key. Now the big trick here is you don't need any random numbers anymore, or you don't need to buy a box which says I make trusted random numbers. You just have to trust that your box is doing what it's supposed to do. The underlying physics there is actually you use this quantum process happening at this beam splitter to generate your random number. So the underlying process to make your random choice is now based back on quantum mechanics. Well, okay. Now this is a little bit of a technical section. We probably are way out of time already. So maybe I mentioned this only briefly. How does that work in practice? That you can actually find the same photons or do a measurement or discuss about the same photons, because the photons come out of that thing randomly. Okay, so it just spits out photons randomly. But you know, whenever such a photon pair is born, they just come out at the same time, and they come out with this, at the same time with about 100 femtoseconds. That's reasonably short. So you can use this same instant of birth of these 2 photons to find them, find the corresponding photons, and that is done. I don't know how to do that by writing down exactly what is the arrival time of a photon at each of the detectors, and we do that with a gadget we have here. I don't know, this is a small USB thing, which just writes down the arrival time of a photon with 125 picoseconds. Okay, that is reasonably short. So then the 2 parties discuss later on, okay, I have seen a photon at 5 o'clock, and I have seen a photon at 5 o'clock plus 10 picoseconds or something like that, and they say that must be from the same pair. Okay, if there's a photon at 5 o'clock and one at 5 o'clock and 10 nanoseconds, then you know, these are 2 different pairs. We don't need to discuss about them. Now for that you need somehow well, at the moment we still need an atomic clock, and I thought I'd just bring along an atomic clock. This is a remarkably boring device. it has not even an on switch, okay? I opened it once, and,
Yes.
and since then it lost its accuracy. So it's like you tell, as a small kid, you're told don't unmount this clock, and then you're just
But it's
left
still
with
enough
this
to
spare
run the whole
wheel or
thing
something
over
like
there.
that. It still works, okay? It still works, but we need an accuracy of about I don't know whether that's this is I don't know, maybe not so smart. You need an accuracy of about 1 part in 10 to the minus 1 part in 10 to the 9, okay? Accuracy of these clocks, such that we can actually identify these pairs.
1 second in 30 years, was it, huh?
Yes, and well, the thing started out in 1 second in, I don't know, 300 years or something like that, and it's now 1 in 30 years. It's actually still more accurate than we would like to have it, because why do you need an atomic clock? And this is kind of a challenge. Maybe I just show how this protocol actually works. So you have your detectors on both sides. This is showing, there's a lot of stupid information. How do we talk about the same time on both sides? We use a little bit of an NTP protocol. Since we're physicists, we cannot do that right, so we thought, okay, maybe half a second is something we get out of that. I guess if you know how to operate that, then people do that with an accuracy of a few microseconds. We are physicists, so we just take the rest out of it using this entangled photon pairs and now atomic clocks, and to get the timing right. And then we just tell the other side, when have we seen a photon? We find out what is the time difference first, and tell the other side, okay, yes, I have seen a photon, and the basis was this and that.
And also, regarding the published source code, the names of the files are actually written onto the line of thinking here.
Don't copy this on your thing. We just put it on a web server. You can look it up and play with it. But you would need all these names of the programs to find out what is doing what. Otherwise, it's just a nightmare to just understand. Yeah, the time difference finding, we need an atomic clock, and we use one of these correlation techniques for mathematicians. This is I don't know, or people who like to play with Fourier transforms. That is a smart way of using a Fourier transform to find a time difference. This is reasonably nice because you need to find this time difference with an accuracy of 2 nanoseconds in half a second or something like that. And that is actually not so easy. If you're interested how this is working, just come by.
If you have ideas, you also come by.
Well, this one works, but we still need an atomic clock for that. But we would just like to run this off a Kuckuck's clock.
Perhaps I should say that we really want to get rid of those atomic clocks, because we use them for 5 seconds every time we run the system, and we're lugging them around. I mean, we brought them from Singapore.
Yeah, and I also like to open them and look what's inside, and then they always go wrong, and so we need to better.
No, but it's really rather frustrating to use them only for 5 seconds and to bring them 10,000 kilometers here.
Yeah. So anybody with a smart idea how to replace that, just come by and just do it. Now, going back to this key distribution thing. For the whole thing to work, for this whole protocol to work, you need to find out, has anybody listened in? Okay, otherwise you cannot really find out whether somebody knows your key. And so you need to do an error correction or an error detection as a first thing, and you do this typically by throwing around parity bits. So if this is the key of Alice and this is the key of Bob, most of the brown bits somehow they coincide, but the red ones they are different. And the way to find this out is Alice sends to Bob somehow parities of these blocks. So here's 1, 0, 0, and so on. And then the other side sends back, okay, I've seen an error, I've seen no error, error, no error, and so on. And if you do that a few times, you can just, first of all, find out where are the errors without revealing all your key. So this is, I don't know, a bunch of 4 blocks, and for every 4 block, you reveal one bit of information. Okay? And you reveal a little bit of more information if you do that to the point that you know finally you don't have any errors left anymore. And then the next step you need to do is you need to make sure that you really remove all the knowledge of an eavesdropper. And this is one of these diagrams which are hard to understand, so I should just probably ask Antija to explain it. What you see here is the fraction of bits. You see a certain error level, okay, and the knowledge of an eavesdropper, okay, and then you can use a mathematical model. What is possible within the laws of physics to extract information out of your key if you see a certain error? Okay, you can just calculate that, and this gives you this curve. And by just correcting all the errors, you just lose some information. So out of whatever 100 bits, you just lose maybe 30% of your bits if you're somewhere here. So, and the remaining rest of the bits is your secret key. Okay, so that is really left as your key material.
So to summarize a little bit, the number of coincidences which we have from the source is not the number of transferred secure key. So it melts down due to error correction, privacy amplification. So yeah, we will see.
Okay, there's one side remark. You also need to do that. I mean, this whole trick works if you have an infinitely large key. Okay, if you have a finitely large key, so 1,000 bits or something like that, it's slightly more complicated, and this is one of the attack methods. But we won't go into that. What I want to go into is you need to do this privacy amplification. So you do. How do you remove that knowledge of an eavesdropper? Okay, so you start with your raw key. Here, my raw key is 6 bits long. Okay, and somehow with my calculations, I know Eve or the eavesdropper could know 2 bits of that secret key, and that means that I have 4 bits of secret information Eve doesn't know out of my 6 bits. Okay, so you need to somehow compress these 6 bits into 4 bits of secret key, and you do that typically with a hash or hash function. And I guess here's lots of mathematicians around who know what a hash function is. Ilya wants to do an explanation because we had also.
Okay, my explanation is, for example, if you have 100 bits and you know that 30 might be known by an eavesdropper, it's only the amount of unknown bit flips which remain as a completely secure information. So 70 bits. So this is privacy amplification. You melt down these 100 bits to 70 bits, which are for sure secure, and the knowledge of an eavesdropper goes to 0.
The parity bit is always allowed to be known by Eve. So part of these bits known by Eve are the parity bits. You always have to give all the parity bits to Eve to begin with. So, pardon? I just don't understand the question.
What if he syncs on the parity bit? Like somehow he gets lucky and lands on the parity bit each time.
Well, it is a statistical process. So by discussing all these parity bits, you reveal a certain amount of information, and you need to make sure that you get a global amount of information you still have left securely, and you need to somehow take that information out of your raw key by using this hash function and compressing it. So a knowledge of a particular key does not help if you use this hash function here. It's like using a document and you change 1 bit, or you know 1 bit, and you boil it down with an MD5 sum or something like that. Then the whole MD5 sum changes, and you do something very similar for this compression matrix here.
Just parity twice or something?
Pardon?
Do you parity multiple times then? Is that
Yes. You do many parity checks, and you keep in mind that every parity bit you discuss about is known to the eavesdropper.
If those are nodes, though, he could potentially reverse that, right?
Maybe this. I'm not exactly sure whether I understand your question, but
I think we should discuss it later on, because now I think we are almost out of time completely, so we have to rush through the rest of the talk. That you get everything out of it.
We just stop at some point, I would say. But yeah. Okay. So what we have set this up and exchanged a key over our campus here in Singapore. Just important things to point out is here the swimming pool. Our physics department is somewhere here, and a few meters above my fridge at home is what was the receiving telescope. The setup you just see outside. If you send light through the atmosphere, you see these blobs of hot air and that wiggles around that photon. When I say photon, I just should say how does such a photon look like? Okay, photon is not a small thing. Okay, our photons, for example, when they are sent through these telescopes, they have a diameter of a few centimeters and a thickness of a few hundred micrometers. So it's like a sheet of paper here has about 100 micrometer thickness. So you can consider all these photons flying around as somehow small pancakes of paper flying with the speed of light to the other side. Well, what we then show to other physicists is how many bits per second or how many accidental coincidences do we have. One thing is we did this at night, okay, because in the morning at 7 o'clock, sunlight comes up and spits lots of photons into our system. And we somehow see all the photons from the sun and not the photons anymore from that source. Ilya is running away already. You end up with a certain number of key bits, okay, this is a few hundred bits per second we get out of that system.